So, hello again students, and welcome to this lecture which will deal a little bit about the resource aspects of different types of biomasses. You will remember the overall structure of the handbook, and you will realize, looking at this matrix, that we shall today deal a little bit with the chapters in column 2, the resources chapters. But before we go into the details of the chapters, or before we introduce the chapters to you, we have to identify a few different crucial words and terms that are used when dealing with natural resources. Natural resources are typically split into three different groups. The first one is the funded resources. A funded resource can be looked upon as a bank account where there is a periodic payment coming in, and from which one can make withdrawals. Since there is a continuous payment into the account or into the fund, you can do a large withdrawal just as long as you manage the fund so that the average withdrawal does not exceed the payments. So you have to balance the fund by balancing withdrawals to payments as an average value. However, for a short period of time, they do not have to balance, but in the long run, they have to balance. Now, biomass is a funded resource. There is an annual growth, an increment of the fund, and we can withdraw biomass from it. Biomass is stored or funded solar energy. It's paid into a fund, and we have to manage that fund, we have to manage the resource so as to make it long-term sustainable. Flowing resources are different. Flowing resources are created and they disappear again. There is no buffer that is filled or emptied for a flowing resource. So for a flowing resource, you have to use it or lose it the very moment it is available. Now, wind and solar energy, just as examples, are flowing energy forms. And solar energy, if you want to use it directly, like in a solar panel or a photovoltaic cell, then you are in the situation to use or lose. But solar energy is also funded and stored in growing biomass. So we can make use of solar energy by managing the biomass resources. The third type of resource are the stored ones. A stored resource is one where the total amount is given once and for all, or indeed for which the periodic increment is negligible, like for the fossil fuels. Stored resources can basically only diminish over time. They are not recreated. So the three kinds are funded resources, flowing resources, and stored resources. And biomass is actually funded solar energy. To make use of a funded resource, we have to manage it in a proper way so as not to exhaust the fund. So biomass is a funded resource, but the annual increment is determined by climate and plant type in combination, as has been outlined in previous lectures and in the course literature. The annual increment is determined by the nutrient and water availability in combination. That is, to put it short, the soil quality and the type of land that is available. And finally, and obviously, the annual increment is determined by the total cultivated area. So these are the things that we have to manage. We cannot manage climate, but we can manage the plant type that we are using. We can choose between basically C3 or C4 or CAM plants, depending on the climate. And we have to make a proper choice. The nutrient balance can be managed. We may use very intensive agriculture, or we may use a very intensive cultivation, whereby we need to add artificial fertilizer to compensate for the nutrient withdrawal with the harvest. The water availability can again be managed. We can go for irrigation, or we can go for the natural water available and the precipitation of the area. So again, there are management parts in the nutrient and water availability. The total cultivated area is a question of land use, and again, this is a question of management and choosing the cultivated area to be used, with respect, of course, also to nutrient and water availability. But the conclusion of this is actually that biomass is not only funded, but it's limited. The availability of biomass is limited, and the annual increment is being determined not only actually by climate and plant types, by nutrient and water availability and the total cultivated area, but it is also determined by the competitive use of land. So biomass cannot be grown on any type of land. There are certain demands on nutrient and water availability, and that means that there will be competitive uses for the land, and that in turn means that the total cultivated area available for biomass for energy crops, or dedicated energy crops, is limited by the competition of land. The overall conclusion of this becomes that any type of biomass for energy demands that each and every process involved in the whole chain, from raw biomass and all the way up to the final energy carrier delivered to the customer, has to have the highest possible efficiency. Otherwise, we do not make proper use of the land that is available on this planet. Also, we have to remember that biomass requires a proper management. So the use of biomass for energy requires management so that we do not exhaust the funds we have available. This is a strict demand for long-term sustainability. Let's now continue and go into the handbook and look at the different chapters. Looking then at the total resources available, it's logical to look first into chapter 0200 and have a look at the table that is down here, table number 1. There are several different estimates of the total potential of bioenergy production or biomass production in the world from a global perspective. And this table was produced in a study from the International Energy Agency. You will notice that in this table, agricultural residues and forest residues are two dominant parts of the production or of the potential, and that they will together or may together create up to about 50 exajoules per year according to this estimate, or even above 200. To this comes then to continue with residues and not go into the potential of energy crops. To this comes potential of dung and organic wastes, which are again significant as compared to the total use of energy in the whole world, which is currently about 500 exajoules. So you will notice that there is a significant potential only in residues. You will also notice that the potential of macro and micro algae is not included in this estimate, because this is still at a very early stage of development. So, summarizing what this table says is that agricultural residues, including dung, are one major source of biomass. Silvicultural residues, like forest residues, are another type of resource. Wastes from society is the third major resource, organic waste. And finally, there is, apart from the agricultural and silvicultural, also a potential of aquacultural biomass to be included into the energy system. Now, this is one of many different estimates on the total resources, and it has to be understood and appreciated that these potentials are very insecure and that different estimates come to radically different conclusions. So what we did previously was, when we looked at the table, was to split the resources into agricultural, silvicultural, aquacultural and societal fractions. But there is another way of looking at it. We can look at it as annual crops, societal, industrial and livestock wastes, of course, and perennial crops. Looking at the resources from these aspects gives us a different set of perspectives, or raises a different set of questions. And that is about the variability. It is obvious that with annual crops there will be an annual variation in the total yield and the total harvest. And this annual variation may be very significant. Now, quite often people mistake the annual availability for the mean annual yield, which is a bit dangerous, because the mean value is per definition a value that is in the middle of the variation span. And that means that if you plan for the use of 100% of the mean annual yield, this actually means that you plan for a supply that every second year is not enough. There will be a deficit of fuel every second year, whereas every second year there will be a surplus. And this means that if you plan to use 100% of the mean value, then what you are actually doing is you are planning for every second year to have to try to raise fuel and raw materials and biomass from some other region, or imported. With perennial crops, this is quite different, because perennial crops will have a more constant growth rate over the years. However, with perennial crops, maybe you cannot harvest every year, so that you will have to rely upon a harvest only on a biennial or triennial basis. So the variations will be less, but you might end up with other problems. There will also be a long-term variation in the perennial crops, depending on the market conditions and on the industrial activity. With the waste fractions from society, from industry and from livestock, there will again be a slow variation in the annual availability and in the amounts available on an annual basis. But most probably the variations will be very much less than with annual crops. So the three different groups outlined here, annual crops, perennial crops and waste fractions, will have a different behavior on a time basis, and obviously also the pricing of them will become different. So this is a little bit of a background to what we shall now be talking about, and let's now turn our eyes to the lignocellulose resources. Concentrating on the situation in Europe, we can see that the total forest resources are outlined in figure 1. The lower left one shows the primary forestry residues. So this map shows the residuals available in Europe from forestry in natural forests. The scale is that the white areas have no data. The dark blue, these are the ones that have the highest potential. The yellow ones are the ones with a very low potential. And the interesting thing about this map is that you will notice how green, dark green, is dominant in the whole continent of Europe, whereas blue and dark blue are dominant in the northern part of Europe. There are also blue areas concentrated in the mountainous areas of the continental climate zone. But it's important to understand that forest residues are actually available all over Europe. Now, primary forests or natural forests are not the only source of lignocellulosic material. And to illustrate that, let's go down a little bit to figure 5 in this chapter. You will notice how this map looks quite different from the one in figure 1 that we just looked at, where the blue areas are dominant in the Mediterranean and southern European area, whereas yellow is in the northern part of Europe. So the colors have switched completely. Now this map shows the potential for energy production from woody residues of fruit trees and orchards, and nuts and berry plantations, olive plantations and alike. It's important to know that the color scale is not the same. So dark blue in this map is only 1/6 of the dark blue in the previous map. But you will still realize that there is quite a large potential of lignocellulosic biomass also in the Mediterranean region, though maybe not from primary forestry, but from fruit tree plantations, from agricultural plantations basically, vineyards, olive tree plantations, fruit trees, nuts, berry plantations, and things like that. This is still lignocellulose. Lignocellulose does not have to originate from forest. But going back to the primary forest and the forest resource, one has to realize that there is a potential conflict between the timber industry and the energy sector. Usually, the trunk of the tree should not even be considered for energy purposes, but sometimes it is, and in that case, obviously, there might be a conflict to the timber industry and to the sawmills. This conflict is, on the other hand, obviously not there when it comes to prunings and residues from like orchards or fruit tree plantations. So this conflict is only present in the case of an expansive wood industry using the forest. However, the use of byproducts like branches, tops or thin trees does not create a conflict to the timber industry. But there are drawbacks with the extraction of branches, tops, and twigs, and foliage and such from the forest. And that conflict is because of the nutrient balance. Generally speaking, one might say that as long as there's only timber extracted from the forest, then the removal of nutrients can be considered almost negligible, because the branches and the tree tops and the foliage is basically left at the felling site, and the nutrients are recirculated. But when the other tree parts are also extracted, like small trees and branches and needles, then there will be an impact on the nutrient balance. And that means that there will be a need for ash recirculation to maintain the nutrient balance, generally speaking. The ashes from the combustion plant should be recirculated to the forest land. There is one exception, and that is basically in the Mediterranean region, where the nutrient losses due to residuals removal are generally preferable to the high nutrient and fertility losses due to forest fires. So the removal of branches, tree tops and residues may be part of a fire prevention action, and that might well be a positive thing to the nutrient balance in the forest. But generally speaking, when planning for the extraction of residues from felling sites, you should consider ash recirculation as a necessary part of the total forest management. The byproducts are discussed a little bit in section 3 of chapter 0201, and they would mainly consist of whole small trees, of adult trees that might have low or no market value, or forest slash, brush as it's also called, which is the branches and tree tops, and obviously the woody vegetation removed in maintenance operations of riverbanks or roadsides or city parks or gardens and the like. The total amounts of these side products may be significant, and you will have to consider the total amounts from a regional perspective when you are investigating the resource balances and the resource potentials of your own region. There are also, as discussed in section 5, byproducts from solid wood industry available. And when you look at these, you should also look at the possibility of pelletizing the residuals, like sawdust, for example, or cutter shavings. This is an excellent material for pelletizing, and it needs to be seriously considered how much the local and regional forest industry or wood industry can contribute to the total fuel supply. Obviously, the main part will be from sawmills, but it has to be remembered also that you cannot use standard numbers to do this type of estimates. The standard numbers might give you anything that the residues from a sawmill, for example, could be anything between 20 and up to more than half of the total volume of input logs into the sawmill. So to really get an estimate, you simply have to go out to the sawmills and try to figure out their actual numbers. Chapter 0201 on lignocellulose resources covers forestry byproducts and agricultural lignocellulose, together with primary wood industry byproducts and secondary wood industry byproducts. But what it does not cover is one significant part of the societal waste fractions, and that is the construction and demolition waste, which is also very often wood and can be basically pure wood. So you also have to include the building sector into your estimate of the total lignocellulosic resources of your region. There may be very significant amounts of construction and demolition waste that is available. When looking at this material, you have to consider, however, that parts of it may have been impregnated with anti-rot agents. It may have been painted, but then other parts will be clean and will well qualify as a clean biofuel once it is chipped and handled. While woody biomass is and probably will remain dominant as a renewable source of energy within the European Federation, there is another one that is rapidly growing, and that is the biogas and the utilization of putrescibles for the production of methane. Now, looking at what's happened in the European Federation during the last few years, the biogas production has risen and is today almost 25 or exceeds 25 terawatt hours per year. And the total, that is the power generation from biogas, and the total energy extraction from biogas or from putrescibles was in 2009 above 97 terawatt hours. So it's definitely a significant contribution coming from biogas, and this is rapidly increasing. The interesting thing about the biogas is the variety of substrates that can be used. Around 52% of the plants running in 2009 produced biogas from agricultural wastes. Landfill gas and sewage treatment plant were together 36%, or about 12% of the total biogas in the EU. The use of biogas is very different in different states within the Federation, as seen from this picture, where the numbers are in megawatt hours per 1,000 inhabitants, or if you feel like that, these are exactly the same numbers as kilowatt hours per inhabitant. And you will realize that the biogas production in Germany is huge, whereas in many other countries, such like Romania, Cyprus, Lithuania, Estonia, and Portugal and Poland, there is very much to be done about the biogas potentials. Going to the top of the chapter and looking at what types of raw materials can be used for biogas production, the chapter treats food residues, wastes from society, wastes from livestock, and resources from landfills. And let's have a look at them from top down. From food residues, the important thing is basically that roughly 1/3 of the edible parts of food produced gets lost or wasted globally. This is about 1.3 billion tons per year worldwide, whereas within the EU, of course, it is much less. But still, almost 1/3 of the total amount of food produced is actually or does become wasted throughout the supply chain. And this food needs to be collected and is an excellent substrate for biogas production. Looking at figure 2, this figure shows light blue how big a fraction of the food losses that are from the production to retailing stages, whereas the brown part of the diagrams shows how much the consumers actually throw away, or how much food is lost at with the consumers. You will realize that in Europe the amount of food waste from households is very significant. And you will also notice that the amount of food losses from the production stages are about double to that from the consumers. So you will need to organize two different supply chains, one based on collecting food waste from the consumers and the households, and one based on collecting waste from the food processing industry, and including the retailers. One second major source of substrates for biogas production is wastewater sludge. And again, this is very significant. However, you have to remember that the sludge has an alternate use as a fertilizer. So more than 2/3 of the sludge produced was used as a fertilizer in agriculture in Cyprus, Spain, Ireland, and the United Kingdom in 2009, that is. It has to be remembered that after anaerobic digestion, what retains in the digestate is the mineral content of the original sludge. Hence, if the fertilizing is after the minerals, then the quality of the digestate is just as good as the quality of the original sludge. Whereas if the important thing for the from a fertilizer point of view was the organic fraction, then certainly the organic fraction has diminished during anaerobic digestion. So depending on what you are after, as for the fertilizer in the sludge, then anaerobic digestion may be completely neutral if you're after the mineral content, or it may lower the quality of the fertilizer, depending, as I said, on what you're after. The third major substrate, or the third major source of substrates for biogas production, is digestible biomass from livestock. That's mainly manure and droppings, and it depends, of course, on how much cattle, how much hens, how many chickens, how many pigs are present in each state. But the total amounts of cattle and animals are huge, and the total potential of manure for biogas production is huge throughout basically all of the European Federation. As for indicative numbers, we can look at table 8. Here you will see that the mean production of biogas, raw biogas this is, in cubic meters per ton of fermentable substance are like 20 and up to over 200 cubic meters per ton fermentable matter, that is. And you will realize that the raw biogas already from the beginning contains more than 50 and up to 60% of methane. So the raw biogas is in itself a fuel. It's a combustible gas with a methane content from 50 up to 60%. This gas can then be upgraded into a vehicle fuel or into basically pure methane. Vehicle fuel quality demands that the methane content exceeds 95%. And this upgrading process is well established and a mature technology that can be bought off the shelf. So the production of biomethane from cattle, manure and droppings is basically a commercial process available already today. There is an ambition within the European Federation to reduce the amount of waste that goes to landfilling. However, there is still significant amounts that are landfilled and deposited, and these amounts will also contain quite a significant amount of organic waste. On average, in the European Federation, 504 kilos of municipal waste was treated per person in 2009, that is. 38% of that was landfilled, 20% incinerated, 24% was recycled, and 18% was composted, as Eurostat puts it. Compost now includes also any biological treatment, so it also includes what is actually digested into biogas. But already from the landfills you can collect biogas by digging down in the bottom of the landfill porous tubes that have holes drilled in them, so that you can extract the gas. This is called landfill gas and has a lower quality than real, quote-unquote, real biogas, but it is still a combustible gas that can be extracted. Doing that extracting this landfill gas, you prevent leakages of methane into the atmosphere. And since methane is a major greenhouse gas component, this has a positive impact to the climate abatement, and it also produces a fuel that can be used in an internal combustion engine for the production of electricity in direct conjunction with a landfill. Continuing with the landfills and the wastes, we can go into chapter 2.4 and have a look at some diagrams at the beginning. The total amount of waste generated in the European Federation exceeds 2 billion tons. 2 billion tons. And out of that, mineral waste is a dominant. However, household waste and similar animal and vegetal wastes are to a great extent organic materials that can be used for biogas production. More than 200 million tons were household waste, and more than 1 million tons were animal and vegetal waste. So these are significant resources that need to be taken care of. The total amounts are distributed basically in the following way: that landfilling, as pointed out previously, there is an ambition to reduce the amount of landfilling, and you will see that there's a downgoing trend all the time since 1995 up until 2009. Incineration is slowly increasing as one way of treating waste. Recycling is rapidly increasing, which is a very good thing, obviously. Biological treatment, which is here called composting, is also a rapidly increasing part of it. But as you will notice, there is still large amounts of material that are landfilled, and that there is room for more of biochemical or biological treatment of organic waste fractions. So here is a huge resource. This figure only talks about or only illustrates the 254 million tons of municipal waste, and does not include what was animal and vegetal waste in these during this period. So you will realize that there is another 100 million tons of basically organic waste to be treated, except for these. Looking now in some more detail at some of the states in which landfilling was the dominant method for waste treatment in 2001, we will find this table, data from Eurostat, where you will see that the total amount in tons per year of household waste in some of the states, such as Hungary, amounted to almost 3.5 million tons. To that comes about 500,000 tons of agricultural waste, making up for a total of almost 4 million tons of waste that is to a great extent putrescible and can be used for biogas production. So the potential is huge. In Poland, we're talking like 8 million tons of waste that could be a resource for biogas production to a great extent. In Spain, we're talking 35 million tons, out of which a major part is actually a potential resource for biogas production. So there is much to be done, and the resources are huge. Looking then at herbaceous biomass and the role that herbaceous biomass can play in the energy system, we find the following. With herbaceous biomass, things are a little bit different, and we can easily distinguish two different groups of herbaceous biomass from agriculture. One is the agricultural residues that are on-field byproducts of the production from food or fiber or feed crops. The other one is dedicated energy crops that are grown as a main product for energy, and there is no other real use for them. The third group are agri-industrial residues, but these will not be treated very much in this chapter. They will only be touched upon. Concentrating first on the agricultural residues, there is one very important factor to estimate the total amounts of them, and that is the residue to product ratio, which is the number of kilos of residues that you get for each kilo of primary product that you produce. The definition of the residue to product ratio is down here, and this is sometimes also referred to as the straw to grain ratio or other similar terms. The ratio of residues to product is obviously crop specific, but it also depends on several other parameters, including, of course, the harvesting technology as such. So therefore, it's not so easy to give fixed values for the RPR, but there are still some indicative values that can be used for a first estimate of the total possible gain in a region. Such values are presented in this table, where you will find the RPR values in the column in the middle. You will notice that the RPR values are, generally speaking, in between 1 and 2, so that for each kilogram of, for example, wheat on the first row that you get 1.3 kilos of residues. So the amount of residues is quite often higher than the amount of the primary product. On the other hand, this table shows you that the lower heating value of the residue are generally fairly low. So, as pointed out before in the lecture about general properties of biomass, the low lignin content with herbaceous biomass gives a low heating value. You will also notice in this table that these residues are very seasonal, and that is a very important factor that makes these residues, the agricultural residues, different from the putrescible biomass that we just talked about, as well as from the woody biomass that we talked about previously in this lecture. Woody biomass, especially industrial residues, are produced on a year-round basis, and putrescibles, like sewage sludge, like cattle manure or droppings from poultry, they are also produced on an all-round year basis, whereas the agricultural residues are produced seasonally and typically during summer or early fall. That means that these fractions are available in large amounts at a certain period of the year. But this is not necessarily the time of the year when you have the highest demand for energy. And hence, these products from agricultural residues need to be stored. But typically they do not suit themselves very well for storing. So the planning and the logistic of the supply chain and indeed of the energy system as a whole has to be affected and to take into account the seasonality of the agricultural residues. You will also notice in this table that many of these different crops yield straw as a main byproduct. Now, straw is quite an important byproduct that has found many different uses in agriculture over the centuries. And that is very clearly demonstrated in this figure, which shows the annual production and use of straw in Denmark for a period of years. You will notice that a lot of the straw is traditionally used for forage and for bedding, while energy purposes and energy straw has come into it during the 1990s and is today an increasing share of the total amount of straw. Provided there is a surplus of straw, there needs not be a conflict between the agricultural use, the traditional use, and the use for energy, but it has to be recognized that many of these agricultural side products have already, by tradition, found their use in agriculture. So the byproduct straw is not worthless, but it has to be considered that it could be used as a green fertilizer or something else. So you have to consider that it has a value and it will have a price. It's not a free biomass. So it is crucial that the total amounts available are big enough to also accommodate energy use. And in this section of the chapter, there is presented a simplified calculation for the availability in the European Federation of two different types of agricultural residues, namely cereal straw and maize residues. This is a very simplified calculation, but it aims only to show how you can do an estimate by simple means. We will not go through it here, but we will just have a look at the result, which is shown in this table. This table shows the cereal straw available for bioenergy in 1,000 tons. So you will notice that, for example, in Denmark, the total amount available is almost 5 million tons of straw. And that is only the amount of straw that would be available for energy purposes. All the other uses are already excluded. In Poland, we're talking 11 million tons. In Germany, 20 million tons. So you will realize that this is quite a huge energy resource. Now, as pointed out, the values in this table are the result of a very simplified calculation. But if we go to another estimate that has been done previously in an EU project, it shows a similar picture. You will notice that the blue and green areas where the availability is high are spread out over the whole continent of Europe. So basically, straw is available wherever you are in the within the European Federation. You will find similar distributions for other agricultural byproducts, not only for straw, as was shown in this example. Looking then at dedicated energy crops, they are a relatively new development in agriculture. And dedicated energy crops are cultivated primarily for use in the energy sector. Now, there are several reasons why energy crops have grown in popularity in recent years, and one major reason being that there have been subsidies to replace food and fiber crops with energy crops. Also, the energy crops do typically have a very high yield of biomass per hectare, which means that provided the price is right, it might be an economic gain for the farmer to actually plant energy crops. More important maybe, some of the energy crops can be cultivated on marginal land and thus bring marginal lands back to the productive economy. The best way to integrate energy crops into farming is to integrate them into a crop rotational scheme, so that the energy crop is used, maybe grown on a field every 3 or 4 or 5 years, so as to help maintaining the productivity of the field and reduce the amount of artificial fertilizers. But in some areas of Europe, energy crops have actually replaced crops for food and fiber production, and that is not a sustainable development. Before we go into the total potential of energy crops, let's just spend a short time looking at the different types that are available. And we can identify mainly 3 different categories, namely the perennial energy crops, which are herbaceous plants for which the life cycle extends over a number of years. The advantage with these is that they require no annual planting, but once they are planted, they continue to grow. On the other hand, this fact, the long lifetime, may seem to some farmers as a long-term obligation to continue to grow them. And so there will be a hesitation to go into this long-term commitment. Also, the perennial crops tend to create quite a tight mat of roots, which might cause that it takes long to restore the field into food or fiber production. Therefore, in some cases, annual energy crops are the easier choice for the farmer. These will include like sorghum, kennaf and hemp, and also some of the traditional crops that can be used, I should say, for energy purposes instead of for food. These include cereals, maize, sunflower and rapeseed, among others. You can actually fire corn, and you can fire sunflower seeds. So you do not have to use the maize or the corn produced from maize actually as food. It can also be used as fuel. But doing that, you have to be aware that what will happen is that the fuel versus food discussion will come up. A third possibility is short rotation copies. This is generally fast-growing tree species that are grown on an arable land and under an intensive management. So that means that the production in tons per hectare and year is very high of these. Again, the problem with short rotation copies is that after a few years you will have a root mat, a mat of intertwined roots in the soil that may take very long to restore so that you can go back to food or fiber production. Having said this, let's have a look at the possible yields. And you will again find a map in the course literature. You will notice on this map that the color scale is different from the map we looked at previously. In this case, Dark blue is only 1/10 of the total amount of energy that it was on the other map showing the availability of straw. So the potential for energy crops is again spread out and distributed all over the European continent and the European Federation, but it is less than the total availability or the total amounts, potentials of straw. So energy crops are really maybe not such a good alternative except in certain areas where a crop can be grown on marginal land and where marginal land is available at great areas. When you read through this chapter in detail, you will of course find much more data and understand very much more than from this very short go-through. But a few important things needs be pointed out. Regardless of the type of resource, agricultural residue, energy crop, agro-industrial residue, or any other type of biomass for that matter, it's not the biomass in itself that has a value in the energy context, but it's the potential to provide an energy service and to produce an energy carrier. Therefore, the total potential may never be expressed only in tons per year, but has also to take the heating value into account. Looking at agricultural residues, dimensioning an energy plant for the mean annual yield will inevitably result in fuel shortages like every second year. Therefore, the planning for utilization of agricultural residues requires that there is a storage in the system, and that storage has to be such that the biomass does not deteriorate too much during storing. You will have to plan very carefully when you want to introduce agricultural residues into the energy system. Actually, the best approach to this problem is to dimension the system considering the total biomass yield to be the mean value minus one standard deviation, and also to assume that the heating value is the mean value minus one standard deviation. If you do that, what happens is that you will be fairly safe to have a full supply so that you will not run into fuel shortages. If you plan according to the mean value of the yield and the mean value of the heating value, then what happens is that you are actually planning for regular shortages of fuel. You should also be aware that for many types of agricultural residues, such as straw, there are already competing and traditional uses as animal feeding, as green fertilizer, as bedding material, etc. And that means that the new bioenergy applications will have to compete with these resources. So there will be a price fight between the traditional use and the energy sector. And you need to consider this carefully before you start planning for an energy plant that shall make use of, for example, straw or whatever. Of course, this does not hold true for energy crops, because for energy crops, they are grown for energy production and not for anything else. So with energy crops, there is not an alternate use. But then, on the other hand, energy crops need to be carefully considered before they are introduced into a region. Because energy crops, setting agricultural fertile land aside for energy crop plantations, you remember the 3.1 football fields? It puts the finger and it puts the focus onto the food versus fuel discussion. And the introduction of energy crops in a given area is definitely not a decision to be taken lightly. You should be very, very careful before you go for dedicated energy crops. However, energy crops on marginal land or energy crops as part of a crop rotational scheme to maintain and maybe even improve soil fertility without excessive use of artificial fertilizers, then the use of energy crops for the energy system and for energy production becomes a sustainable solution and part of a sustainable future. So be very careful before you introduce energy crops, but be aware of the opportunities to use agricultural residues. That would be about this, about the resources. So goodbye for now, students.